Welcome, HOD sir, JP Mishra.
HOD sir, welcome sir. Mishra sir. Good morning, Mishra sir. Can you hear me, sir?
Yes, we can hear. HOD sir, good morning.
Your voice coming out now.
Sarpan sir, good morning.
Sir, unmute yourself, then say then.
Yeah.
Unmute yourself, then. If
Good morning, Gurunath sir. Welcome, sir.
Hi, good morning.
Good morning, sir. Sir, another one more program is also going on. That inauguration started at 9:30. So director and everybody is there. I think they will join by 10:15.
Okay, sure.
Thank you, sir. Good morning, sir. Ali Ahmad, sir. Good morning, sir. Can you hear me what I am telling?
Yes. Mic off.
Please.
Good morning, sir.
Morning.
Yes, sir.
Fine, madam. Fine.
This, we may call to director start. Other program, inauguration of other program is already over.
Okay, we'll call, sir. Yeah, we'll call now.
Yeah.
Okay, sir.
Welcome, sir.
Welcome. Morning.
Good morning, sir. Can we start, sir?
Yes, please.
A very good morning and warm welcome. A very good morning and warm welcome to our Honorable Director of National Institute of Technology, Silchar, Professor Sivaji Bandyopadhyay. Our chief guest and eminent speaker, Professor Sathans from NIT Kurukshetra. Our invited guest and eminent speaker, Dr. Rabiul Islam from UOW, Australia. Our invited guest and eminent speaker, Dr. Gurunath Gurela from IISc Bangalore, Professor M. Ali Ahmed, Dean R&C from NIT Silchar, Professor A.K. Barguria from NIT Silchar, Dean Academic, Dr. Sukumar Pati, TechCube 3 Coordinator from NIT Silchar, Dr. J.P. Mishra, Head of the Department of Electrical Engineering Department from NIT Silchar, Deans, Heads of various departments, faculty members, and my dear participants from India and abroad. I hope all of you are well and safe in this pandemic situation. On behalf of the organizing committee and the other coordinators of this short-term training program, Dr. Asha Rani, Dr. Amritesh Kumar, Dr. Awadpati, I, Jeevan Jot Singh, welcome you all, and I would like to express my heartfelt gratitude for your presence in this inaugural ceremony of the one-week short-term training program on power electronics applications to industrial systems, organized by the Department of Electrical Engineering Department, NIT Silchar. Once again, I would like to welcome all the dignitaries and participants gathered here and wishing you a good day. Now, I request my co-coordinator, Dr. Asha Rani, to give a brief note on the short-term training program.
Thanking you, Jeevan sir, distinguished dignitaries, our Honorable Director of National Institute of Technology, Silchar, Professor Shivaji Bandyopadhyay sir, our Chief Guest, Professor Satan sir from NIT Kurukshetra, our invited guest, Dr. Renewable Islam sir from University of Bologna, Australia, Dr. Gurunath sir from IISc Bangalore, Dean Research and Consultancy, Professor M.A. Ali Ahmed sir, Dean Academic, Professor A.K. Barbia sir, TechUp 3 Coordinator of NIT Silchar, Dr. Sukumar Pati sir, our beloved Head of the Department of Electrical Engineering, Dr. J.P. Mishra sir, Deans, Heads of various departments, my dear colleagues and dear participants of the one-week short-term training program on power electronics application to industrial systems from India and abroad. A very good morning to one and all present here. About the program, basically owing to the escalating demand for energy, depleting fossil fuel reserves and growing concerns over environmental degradation have brought in new paradigms in the global perspective and has fueled efforts towards the development of renewable sources that have a lesser footprint on the environment. The advent of power electronics plays a significant role here in efficient extraction and feeding of clean energy from renewable sources like solar and wind to the grid while taking care of the grid stability. However, there exist concerns in integration and control of these renewable sources with the conventional grid or microgrid. In addition, though PV modules are cheaper, there is a desperate need to maximize the extracted energy to compromise for the huge capital investment for the PV power plants. Also, the solar PV systems installed in outdoor environments are susceptible to partial shading and degradation as well. So similar is the case with wind generators integrated with the grid also, because of the intermittent nature of the wind and due to the frequent power quality issues persisting in the grid. So these factors are damaging the energy yield, and this is high time to address these challenges to open doors for several active areas of research. Also, we can see there's a prominent drift in the recent years towards the distributed energy systems and integration of renewable energy sources to the autonomous microgrid or nanogrid, which require specific power electronic applications for the reliable and secure operation of the power grid. Furthermore, the emergence of and integration of electric vehicles with the AC-DC grid, which will be quite common in the near future, which also needs sophisticated control techniques. So here plays a noteworthy role by the power electronic converters. In this context, this course is designed to address the various design, operational, and control aspects of advanced power electronic interfaces associated with microgrids, with different sessions on multi-level inverters for renewable power applications, modeling of PV cells and control of grid-connected PV inverters, effect of partial shading and interconnected schemes for PV systems, FPGA-based control of grid-tied photovoltaic systems, design of solar-based inverters, critical measurement challenges and testing of new generation power electronic devices, intelligent control and applications in microgrid, realistic experimental test beds for micro and smart energy systems, challenges involved in hybrid microgrids, control of grid-connected wind generators, power electronics in EV, high-speed reconfigurable power electronic controllers, design and application of proportional resonant controllers, etc. So all these sessions will be handled by our eminent academicians from reputed universities across the country and abroad, which include faculties from IISc Bangalore, NIT Kurukshetra, NIT Trichy, NIT Surathkal, NIT Silchar, PEC Chandigarh, University of Bologna, Australia, and from Aalborg University, Denmark. In addition, a few of these sessions will be handled by industrial experts from CDAC, Tektronix, Integral Technologies, and Sapro Electronics Electrical Limited as well. We believe that this course will definitely enlighten the participants with fundamentals, latest findings, and practical challenges, and the possible solutions pertaining to grid integration of solar photovoltaic systems and wind energy systems and EV charging infrastructure, such that they can further explore and bring forth innovative ideas which can set benchmarks for the future research. Moreover, this workshop will also facilitate in enabling technical interactions between the research groups from various industries, paving the way for an overall fortification of technical capabilities of the new power electronics community. So about the total number of registrations we received for the program, it is actually 2,304, of which we have shortlisted 2,273 participants. This includes 648 faculties, of which 634 faculties are from India, which include faculties from different NITs and government and autonomous engineering colleges across the country. And we have 14 faculties from abroad, which include faculties from Bangladesh, Deakin University, Australia, Firat University, Turkey, from University of Granada, University of Chile, University of Colombia, School of Electrical Engineering, Serbia, and from Nepal also. Also, there are 131 industry delegates who are participating in the program, out of which 119 are from different reputed industries within India like General Electric, NPCIL, MTRDC, CDAC, BARC, Central Electricity Authority, Siemens Technology Services, Suslon, Gujarat Wind Park, etc. And there are 12 industry delegates which are participating in the program from Bangladesh, Germany, Nepal, Russia, and from Saudi Arabia also. And moreover, we have 1,494 students registered for this program, of which 1,457 are from India and 37 are from abroad. So this includes PhD students from Germany, Turkey, Indonesia, Egypt, Bolivia, Iraq, Bhutan, Bangladesh, Malaysia, etc. So the relevance of this SCTP theme in the present research scenario can be seen from the registered participants across the globe. We, NIT Silchar, wishes all the participants a fruitful week ahead, which will enlighten you with innovative ideas for your future research. Thank you all. Have a good day. Now I am handing over the session to my co-coordinator, Dr. Amritesh Kumar sir. Sir, please.
Thank you, madam. Now I'd like to invite our beloved HOD, Electrical Engineering Department, Dr. JP Misra, for the welcome address. Sir, please.
Thank you, Dr. Amritesh and Dr. Asharani. A very good morning to one and all present here. Honorable Director, NIT Silchar, Professor Shivaji Bandyopadhyay, Honorable Chief Guest and External Expert, Professor Sathan from Department of Electrical Engineering, NIT Kurukshetra, Honorable Guest and External Expert, Dr. Gurunath Gurala from Department of Electrical Engineering, ISC Bangalore, Honorable Guest and External Expert, Dr. Rabul Islam from School of Electrical and Computer Telecommunication Engineering, Faculty of Engineering and Information Science, University of Wollongong, Australia, respected Dean Research and Consultancy, NIT Silchar, Professor M. Ali Ahmad, respected Dean Academic, NIT Silchar, Professor A.K. Barbuya, respected TechIF3 Coordinator, NIT Silchar, Dr. Sukumar Pati, esteemed faculty colleagues, dear participants from different teaching institutions as well as industry. International short-term training program on power electronics application to industrial system sponsored by TechIF3 NIT Silchar. First of all, we are very thankful to our director, Professor Shivaji Bandyopadhyay, for sanctioning the short-term training program for the Department of Electrical Engineering with full-fledged support from our TechIF3 coordinator, Dr. Sukumar Pati. As cited by Dr. Asharani, the coordinator of the workshop, various international and national level experts, including few internal experts as well as who are going to deliver various relevant topics which are mainly focused on to discuss how the power electronics plays a significant role in efficient extraction and feeding clean energy from renewable energy sources like solar and wind to the grid without hampering the grid stability. However, there are various challenges or issues are faced while integrating and controlling renewable sources with the conventional grid and or microgrid under varying source conditions, non-ideal grid conditions, as well as varying linear and non-linear loading conditions also. So I hope several issues will be addressed under the topic of grid synchronization of distributed energy system, distributed generation system. Also, another aspect, the recent trends towards the distributed energy systems and integration of renewable sources to the autonomous micro and nano grids, which require specific power control applications and power electronics control capabilities for its reliable and secure operation. Further, relating to the transportation industries, the emergence and integration of electric vehicles with the AC and DC grids also needs sophisticated control using various power electronic converters such as resonant converters, voltage source inverters, as well as DC-DC converters. And another important aspects also which are going to be covered in this short-term training is the high-speed reconfigurable controller, which provides an optimized environment of software and hardware for real-time control of power electronics based system on a programmable chip design methodology. This controller is realized in a field programmable gate array using integrated soft CPU's code, and a cost-effective alternative to conventional controllers, like microcontrollers, DSPs, which have got limited resources as well as become obsolete faster. Therefore, this course is designed to address various designs, operational and control aspects of advanced power electronics interfaces associated with microgrids. Presently, we have with us Honorable Chief Guest and External Expert Professor Satans from NIT Kurukshetra, Honorable Guests and External Invited Experts Dr. Gurunath Gurala from IST Bangalore, as well as Honorable Guests and External Expert Dr. Raibul Islam from University of Wollongong, Australia. I thank you for joining this inaugural function as well as for accepting our invitation for delivering talks with your intense expertise to make this program more interesting and informative. As informed by the coordinators, there are more than 3,000 participants registered. However, they are shortlisted with 2,270, including the faculties, industry delegates, and students from across the India and as well as abroad. Hope this small short-term training program may provide unique opportunity to all in developing the new ideas and avenues for doing research in power electronics based control in renewable and electric vehicle applications. My best wishes to all the course coordinators, Dr. Jivanjot Singh, Dr. Amritesh Kumar, Dr. Asarani, and Dr. Awadpati, and also to entire team of the short-term training program for a very grand success of this program. Okay, thank you all again. Over to Dr. Amritesh.
Thank you, sir, for your kind words and for supporting us to organize the program in a professional way. Now I'd like to invite Dr. Sukumar Pati, JQ Coordinator, NIT Silchar, to address the gathering. Sir, please.
Yeah, thank you, Dr. Kumar. Good morning to one and all. Respected Director Sir, respected Professor A. Mali Ahmed, Dean Research and Consultancy, Professor A.K. Barguya, Dean Academic, Professor Satans, Dr. Rabiul Islam, Dr. Gurunath Gurala, distinguished speakers for this international short-term training program, Dr. J.P. Mishra, Head Electrical Engineering Department, my esteemed colleagues from NIT Silchar and other institutes, dear participants. At the outset, on behalf of Coordinator Techie 3 NIT Silchar and my own behalf, I congratulate all the coordinators, Dr. Asarani, Dr. Jivanjit Singh, Dr. Amritesh Kumar, and Dr. Awadpati for their initiative and untiring efforts to conduct this international short-term training program. I am sure that all the participants attending this short-term training program will learn the useful and relevant information about the power electronics applications to industrial systems. I firmly believe that this short-term training program will impart useful knowledge to the participants so that they can promote research activities in the field of power electronics. Moreover, undergraduate students attending this short-term training program can effectively utilize the knowledge for their higher studies and future engineering career. Most of the programs held during these pandemic situations under Techie 3, including this one, is now streaming live through official YouTube channel of NIT Silchar. It is heartening to share that in August 2020, the number of subscribers has increased to 1,529 with total views of 68,120, and the total duration of view is 8,13,498 minutes. This statistics itself reflects the success of conducting short-term training program And I believe that with this, the peer perception about NIT Silchar can be improved to a greater extent. Once again, congratulations to all the coordinators and all the participants. I wish a grand success of this international short-term training program. Thank you.
Thank you, sir, for your inspirational words, support from the beginning of this program. Okay, so now I'd like to invite Professor M. Ali Ahmad, Dean RC, NIT Silchar, to share his views about the program. Sir, please.
Thank you, Amitesh. Thank you very much. Very good morning to all the delegates present in the meeting. Respected Professor Shivaji Bandyopadhyay, Director, NIT Silchar, Professor Sathans from NIT Kurukshetra, Professor Rabiul Islam from University of Bolong, Australia, Professor Gurunath Kurala from ISC Bangalore, all the galaxy of experts from India and abroad, Dean Academic NIT Silchar, Professor A.K. Bonvia, Professor Sukumar Poti, Secretary Coordinator NIT Silchar, Professor J.P. Mishra, Head of the Department NIT Electrical Engineering NIT Silchar, all my esteemed colleagues from NIT Silchar and other institutions across the country and abroad, and all the national and international participants for the auction. I welcome all of you to this 1 week short-term training program on power electronics application to industrial system conducted by Electrical Engineering Department. So from the statistics that has been presented by the coordinator, I hope the workshop will definitely give an impact internationally and will be a successful one. I will request all the participants just to explore the possibility of devising their topics or area on which they will do the future research and make a bonding with the expert, maybe from NIT Silchar or from other institutions nationally and internationally. As you know, friends, nowadays it is the day of interdisciplinary research, and this is one area where the interdisciplinary research can be conducted very effectively. I will request the head of the department that by today or tomorrow I will be able to send the list of newly admitted candidates to you, if not done till today. And I request all the head of the department to give the information to this newly admitted PhD student to join the workshop so that they can gain sufficient knowledge to decide their field of future research. With this, again, I wish the workshop to be a successful one. I thank you, everybody. Over to coordinator. Thank you, sir.
Thank you, sir. As soon as we receive the list of the newly joined PhD students, surely will share the link to them also, sir. Okay, so thank you, sir,
Yes,
for being
thank
present here in your busy schedule and enriching us with your words of wisdom. Now I'd like to invite Professor A.K. Barbhuiya, sir, Dean Academics, to share a few words about the program. Sir, please.
Good morning, respected Director, Professor Shivaji Bandyopadhyay, sir, our Chief Guest, Professor Sathans from NIT Kurukshetra, Dr. Rabiul Islam from University of Bolong, Australia, Dr. Gurunath Kurala from ISC Bangalore, my colleague Professor Muqaddas Ali Ahmed, Dean RNC, Dr. Sukumar Pati, Coordinator Technic 3, Dr. J.P. Mishra, Head Electrical Engineering Department, experts from India and abroad, and other colleagues. So again, good morning to all of you. Now, regarding this short-term training program, power electronics application to industrial system. I am not very much related to this area, but whatever I have learned from this present deliberation, head of the department has explained the various application of power electronics, including its application in the reliable, efficient power supply, storage of renewable energy, also integrating the renewable energy to the existing grids. So these are very much hot topics. With the demand of electricity, we must increase the efficiency and reliability of the power system. Now, I am sure that the participant will greatly benefit from this course. They will have chance to interact with the experts from academia as well as from industry. They can shape out their research projects and also the future specialization of studies in this field of electrical engineering. So I am very happy that this electrical engineering department, probably this is the 4th course they are conducting in these difficult days. So I congratulate all the coordinators and the head of Department of Electrical Engineering for their continuous involvement in these types of seminar, workshop, and this is enhancing the visibility of NIT Silchar. So with this few words, I wish a grand success of this training program. Thank you. Over to Amritesh.
Thank you, sir, for being part of this program and for the wholehearted support extended to us. Now I'd like to invite Honorable Chief Guest and expert speaker, Professor Satan sir, to say a few words about the program to our participants. Sir, please.
Namaskar and a very good morning to all of you ladies and gentlemen. I hope I'm audible to you.
Yes, sir.
Yes, sir.
Okay, thank you. Respected Professor Bandyopadhyay, the Honorable Director NIT Silchar, Head of the Department, Professor J.P. Mishra, TechUp Coordinator, Dr. Sukumar Pati, all esteemed Deans of NIT Silchar, the organizing committee members, and the young coordinators of this short-term training program, the team, Dr. Jeevan Jyot Singh, Dr. Asha Rani, and Dr. Awadh Pati, and Dr. Amritesh, all other faculty colleagues from NIT Silchar, and BA participants. In fact, it's a real pleasure to be a part of this inaugural function and to be joining this August gathering on this inaugural function of this short-term training program on a very important topic of power electronics applications to industrial systems. And I feel privileged, in fact, to have been given this honor in certain capacity that I'm here today, this morning. And in fact, I congratulate right away the organizing team and the institute, the director, and everybody connected for this wonderful event in such a huge response that I got to know from the organizers when they were briefing. The response is really very huge. It's 2,000 plus number of participants, and that's commendable work. So I appreciate the tremendous work the organizing team has done, the coordinators have done, and as I understand, the participants are from academia, from industry, from within India, from outside India. So that speaks of the volume, the kind of effort the organizing team have put up. So I'm really very glad to know that, and the short-term training programs of this magnitude, to be honest, have not come across, until now, wherein the participation is such a huge number. So congratulations to the team. And under the able guidance of the Honorable Director, in fact, I think all the young faculty members, with the guidance of the senior colleagues, they are doing really good. That's what I got to understand, during my interactions with the Honorable Director, Professor Bandyopadhyay. So I think that can happen only when you get the support right from the top. And that's what, I think the institute is lucky enough to have a director like Professor Bandyopadhyay, who supports this kind of activity, who supports all academic ventures, that you come up with. So because of that only, this could be possible. And obviously, TechIP is a good support, wherein a lot of academic activities can be conducted. So that way, TechIP is also playing its vital role. And I'm very encouraged to see, so many renowned experts, not only from within India, but even from outside, from abroad, being a part of this program, who would be delivering the talks and who would be interacting with the participants. And if I was going through the list of experts, so I could, that speaks of the kind of quality and quantum of knowledge that possibly we can look forward to, in this short-term training program. So from that point, I'm really, of the firm belief that this event or this program is going to be really very, knowledgeable experience for the participants, very enriching experience for the participants, and a lot of, interaction will take place. A lot of networking possibly can take place through this program. And so far as the theme of this program is concerned, it's very apt and very contemporary, power electronics applications. So if you talk of sustainable energy, at some of, I think that Dr. Awadpati was talking while she was briefing, sustainable energy, when we talk of in terms of electrical engineering or electrical energy in terms of electrical power, we do have the renewables, they are penetrating the power system in a big way. We talk of maybe PV, we talk of wind energy, we talk of tidal energy, we talk of, any other form of energy, biomass energy, whatever. So renewables, in fact, is the future. And when it comes to utilizing the renewable sources of energy for electrical power generation, there are a whole lot of issues involved in that. There are associated challenges involved in that. And those challenges around, say, ensuring the stability of the grid, ensuring, that the quality of power is good. So that is where power electronics, has a very important role to play. Without power electronics, I think we can't think of utilizing or exploiting these renewable sources of energy. So power electronics is there to, there's a whole lot of, conversion and inversion of power that takes place when we use renewable energy sources. And yes, there was this concern when Dr. Awadpati was briefing that due to the fossil fuels getting depleted, that is one reason, yes, of course, one of the important reasons. But then more important nowadays is the environmental concern. We are really very worried about the degradation of the environment, that is happening because of the conventional energy sources. So environmental concern is number one concern. Then I think the concern of depleting fossil fuels. And may possibly, while we'll still have sufficient reserves of these fossil fuels, we'll stop using them. Right, that's the importance of environmental concerns. And likewise, with the Stone Age, didn't end because of want of stones. We still had, sufficient stones, but we moved to another age. Likewise, we'll have these reserves available with us, fossil fuel reserves. We'll stop using them. We'll switch over, obviously, to the renewable energy. And ideally speaking, if everything goes fine, the way technology is evolving, the way efficiency of these PV and wind, generation systems is improving, and the way, the prices are coming down. I mean, it's no more, very heavy or very costly equipment if you talk of PV or wind or whatever. So I think we can ideally see a world powered fully by renewables by maybe some 2-3 decades or 4 decades down the line. And every government around the globe, they're doing really a lot of focus is there on renewables. And even in our government, we are setting our targets. You might be all knowing that 175 gigawatt by 2022, and possibly we'll achieve even earlier. So that's the hope. Power electronics, in a way, is going to be playing a very crucial role in improving the efficiency of these renewable sources or renewable generation. It's going to play a very important role in ensuring the quality of power, control that is to be exercised, stability of this, integration of these renewables into the grid. You talk of any domain, power electronics is there. And because of that only, this whole lot of progress. And the intermittency of these renewable energy sources is a major concern. The unpredictability is a major concern, and because of that, we do require certain energy storage systems. Right, and when we use energy storage systems, again, the energy has to be injected into the system, into the grid, or else extracted from the grid when it's other way around. And that is where again we need power electronics. So power electronics, applications to industrial systems, and primarily with reference to the electrical engineering to sustainable energy or maybe renewable energy sources, is very pertinent. And I'm sure, given the magnitude of this short-term training program in terms of the participation or in terms of the kind of connecting very wonderful speakers to the event, I think it's really very huge, really very wonderful. And these for 5 or 6 days event, I'm sure would be really a very enriching and very knowledgeable experience for every one of us, those who are the part of it. And so without taking much time, I'll simply say a wonderful effort by the organizing team, wonderful guidance by the senior colleagues to the youngsters, and absolutely wonderful vision coming and the support coming from the very head of the institution. So congratulations to one and all involved in this, and congratulations also to the participants to have registered in such a huge number, for showing such a keen interest in this. So with that note, congratulating you all. Thank you so very much for inviting me all.
Thank you, sir. Thank you, sir, for sharing your valuable thoughts with us and for accepting our invitation to be a part of this STTP program, even in your busy schedule. Now, I'd like to invite our honorable guest and expert speaker, Dr. Renewable Islam from UAW, to say a few words about the program. Sir, please.
Honorable Chief Guest, Special Guest, Director of NIT Silha, respected deans, head of the department, TQIP coordinator of this training program, and dear participants, good morning and welcome to the training program on power electronics applications to industrial systems. It is my pleasure to be involved with this training program. Special thanks to Dr. Amitas Kumar for his collaboration with me, as well as with the University of Wollongong, Australia. I believe this is a timely training program, as well as the power electronics are becoming one of the essential part of our modern life. As well as achieving sustainable development goals, I hope participants will be benefited greatly from this training program, as the program is addressing many emerging technologies related to power electronics and their applications. I wish every success of this training program. Thank you all.
Thank you, sir, for your inspirational thoughts shared with us and for taking the pain and accepting our invitation to be a part of this STP. Now I would like to invite honorable guest and expert speaker, Dr. Gurunath Gorela, to say a few words about the program. Sir, please.
Thank you. Very good morning. Can you all hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Thank you. So I can see that very senior professors are here, and so whatever I'm here doing today is because of committed teachers like you. So please accept my traditional namaste to all of you. And I welcome there are variety in the entire program structure. So people are talking from renewables to electric vehicles and high-speed converters and all that stuff. At the end of the day, if you want to approach any power electronic systems, there are some fundamental things that you need to look at. There are three components in any power electronic system. First thing is modeling. Second is simulation. And the third one is implementation and experimentation. Without these three things, you cannot actually take a power electronic system from a lab to an industry. And remember, you are the people who are going to do the future power electronic systems. And if you want to do that, and you want to make yourself an expert person to be established in that, then I want you to focus in everything that is being discussed in this program. I want you to focus on these three and understand and assimilate the knowledge. For example, if you talk about modeling, in the modeling, any power electronic systems has only 4 components: a resistance, inductance, capacitance, and a switch. How do they interact is what is called as topology. And you have to understand the topology and how the input translates from to the output. And if you understand that, then I think you understood the complete concept about how that particular circuit is working. And for that, you should know how to solve the ordinary differential equations so that you will understand how the waveform will look like. And you will be able to understand what kind of harmonics you may see in it. If I see more harmonics, then you have to make sure that you have to reduce the harmonics. Then you need to understand again different types of filters, different types of pulse width modulation techniques, so that you can actually achieve what is needed as per the industry standard. So all these are linked to each other, and everything you should have a very good command. For example, you should know how to solve differential equations. You should know how to solve algebraic equations. You should know how to use Fourier series to analyze your circuits. These are all very fundamentals, which you have already learned in your BE and undergraduate, or even by 10th standard, you have learned a lot of things, and you will be applying that for a cause. So this relationship you should be able to understand. And when you talk about simulation, remember, unless you implement it on an embedded system, then you will never be able to take it to the industry. Today, for the sake of reducing your burden, many colleges adopt taking some existing controller, do a simulation in MATLAB, and put it onto an embedded controller and do it. And I'm telling you, it is not going to help you for the industry to go forward. Okay, and I want all of you to focus on one programming language, that is C, which is used in all the embedded systems, so that you can implement by yourself, or you learn FPGA, which is also a platform which is being used. And that is your goal, and you should actually achieve that by yourself. And the last part is implementation and experimentation. Unless you make your hands dirty, you will never be called as an expert. Let me tell you one thing. Let's say if you want to do cooking, and unless you make first attempt of making something which is eatable by everybody, then you will never try to do another item, right? So the first step is to learn whatever something in a meaningful way. Once you learn, then you automatically try yourself. Okay, let me try another dish. Let me try another dish. This is where actually the innovation comes. Many people start from innovation. I will take some idea and then start doing all these things. That way it doesn't work. You should first learn how to do things very well. Automatically innovation will come, because innovation is already there in every human being. We always try to be innovative. We always try to be innovative in making our dress different, how we talk different. So innovation automatically comes the moment you become expert in all these 3 areas. So hopefully, I hope that all the speakers will talk about so many things. Don't get perturbed by so many things. Oh, so much is there. But if you start thinking everything in these 3 lines, modeling, simulation, and implementation, and you will be able to understand any advanced topic in a very, very well. And I request you all to focus on that. And thank you so much for giving me this opportunity. And once again, congratulate the team members and all the participants. Thank you very much.
Thank you, sir, for your esteemed presence here in this STTP and for accepting our invitation in your extremely busy schedule. Now it is my privilege and honor to request our Honorable Director, sir, who is also the patron of this short-term training program, Professor Shivaji Bandyopadhyay, to address the gathering. Please, sir.
Yeah. Very good morning to my colleagues, Professor Satans, Professor Islam, Professor Gurala, the other distinguished experts from abroad who may not be present in today's inauguration program, my colleagues from NIT Silchar, other institutes across India, the PhD scholars, and the undergraduate and the master students. It's nice to see that the number of participants in the today's program, so that has crossed, say, the standard mark of 2,000. And from this, it appears that even after the pandemic situation goes over, we will be continuing with this type of short-term training program or webinars on the net, because otherwise physically for people from so many parts of the world and so for so many dignitaries, it would not have been possible to make the program a grand success in this way. Now, as far as the institute is concerned, it is just for sharing with all my colleagues and the scholars also. That is, we have put research and innovation as our key guiding principle. And by research and innovation, we focus on interdisciplinary work, collaborative work. We focus on internationalization, because with internationalization comes innovative problems. So that requires innovative solutions at the same time. And obviously, we need collaboration with the industry as well. In order to carry forward our objectives on the research and the innovation arena, we have the Undergraduate Research Council, where we inspire the undergraduate students and support them with funding from the institute to take up research in the cutting-edge technologies being mentored by their own faculties. And we have put the Sustainable Development Goals of the United Nations as our guiding principle in all our teaching, learning, and as well as the research activities, because we understand that is as academicians and we ourselves and our scholars and the students need to serve the society, and the 17 sustainable goals from United Nations in the areas of, say, energy, environment, and other areas. So with that as our guiding principle, we will be able to solve that is, take care of the problems that plague the society. As a measure of that, as a measure of our travel towards the research and the innovativeness, in the last 2.5 years, we have basically doubled the number of PhD scholars in the institute, because with increase in PhD scholars, our colleagues can work in new and new areas, new and new multidisciplinary and transdisciplinary areas. And as our Dean RC Research Consultancy was sharing, that is today after in the afternoon. So we'll be sharing this link, and for the future, this training program links with our PhD students, so that they also get benefited and they become part of the exercise as well. Now, in our pursuit of research and innovation, so we have been able to receive some modest ranks at the national as well as at the international level. They basically, that is, we take part in the ranking, not only for the sake of receiving the ranks basically, but to assess our position. That is where our strengths lie, where our weaknesses are, where are our opportunities to go ahead, and what are our challenges, so that we can plan our activities in that way, and we can proceed for the future. Now, as far as this 1-week international short-term training program on power electronics applications to industrial systems is concerned, first of all, the program is truly international in nature, with participants, that is the speakers from across the globe, participants also from various parts of India as well as from abroad. And the area is truly interdisciplinary in nature, because power electronics provides the drive actually for the various the systems with solid state electronics at the background, and for areas like renewable energy, electrical vehicles, high speed drives, and so on and so forth. So it has a role on the manufacturing area also to provide the self-reliant support to the self-reliant India. And I wish that uh, already a lot of collaborative activities are going on between NIT Silchar and other institutes across the globe and within the country in these areas of power electronics. And I wish that more and more opportunities and collaborations will come up. And I wish that the PhD students and the undergraduate and the other students who are joining the program, they also take the cue from that. And those who have, say, identified their research problem, you identify or find out, say, which area you need to listen to or whom you need to contact with. Those who are in the area of the identifying their initializing their PhD problem. So you try to listen to as many things as possible so that you can come up with an area of your identification or choice. And obviously for the industry people also to identify that is what are the institutes, including NIT Silchar, where the collaborations can take place. Because otherwise, in a place like, say, Silchar, say, we normally sometimes feel the challenge of that is the relationship with the industries, because industry people say does not always find the interest to interact with us. But I believe that with our expertise in the various areas and state of the things, more and more collaborations and more industry level projects will come up in future also. With this, I wish the program a grand success. Thank you.
Thank you so much, sir, for your words of wisdom and inspiration as always. Now we have come to the end of this inaugural function. I am very pleased to thank all the guests for attending this inaugural ceremony. Now I would like to invite Dr. Awadpati, coordinator of the short-term training program, to propose a vote of thanks.
Thank you, Amrish. A very good morning to one and all present here. Honorable Director, Professor Shivaji Bandyopadhyay, Dean RNC, Professor M. Ali Ahmed, Dean Academic, Professor A.K. Baghuiya, EQ Coordinator, Dr. Sukumar Pati, our invited guests and eminent speakers, Professor Sathans, NIT Kurukshetra, Dr. Radul Islam, University of Wollongong, Australia, Dr. Gurnath Gurala, IISc Bangalore, and my dear Honorable HOD, Professor J.P. Mishra, sir, my dear colleagues and dear participants, it's my privilege and immense pleasure to propose vote of thanks in the inaugural ceremony of 1 week short-term training program on power electronics applications to industrial systems, organized by the Department of Electrical Engineering, NIT Silchar. On the behalf of organizing committee and on own behalf, I express my sincere thanks to Honorable Director, sir. Sir, we are grateful to you for your presence and words of encouragement. Your able guidance and support always make us think beyond in both academic and research activity. We thank you very much for your suggestion and continuous support in every aspect. Thank you, sir. Now we extend our gratitude to our Dean RNC, Professor M. Ali Ahmed, sir, for his valuable time and constructive suggestions for organizing this program. Thank you, sir. Now we extend our gratitude to our Dean Academic, Professor A.K. Baghuiya, sir, for his motivational words and supports in conducting this FDP. Thank you, sir. Now we can extend our gratitude to Dr. Sukumar Pati, EQ Coordinator, NIT Silchar, who has given us to consent to organize this short-term training program and also for providing us with the necessary financial support to conduct this program. Thank you so much, sir. Now we would like to extend our sincere thanks to gratitude to the invited guests and honorable speakers, Professor Sathans, Dr. Rabiul Islam, Dr. Gurunath Gurala for sparing their valuable times with us with their motivational words in inaugural function and for all agreeing to deliver the lecture during this STTP. Thank you, sirs. Now we would like to extend our sincere thanks gratitude to our beloved HOD, Dr. J.P. Misra, sir, and our ex-HOD, Professor NVD Chaudhary, sir, for their valuable suggestions and guidance to organize this workshop. Thank you, sir. Also, we acknowledge the help and support provided by our institute, NIT Silchar, and also by our Department of Electrical Engineering. Now, I would like to thank my colleague, research scholars, students, and my dear participants from our organization and abroad, and our institute also for their presence in this inaugural function. Thank you all. Over to Jeevan.
Thank you, Awad sir. Now, this is an opportune time to officially declare the short-term training program is open. So I request our Honorable Director of NIT Silchar and Chief Patron to declare the short-term training program is open.
Yeah. So I declare the 1-week international short-term training program on power electronics applications to industrial systems open. Okay, thank you. Thank you.
Thank you, sir, once again, and thank you all for attending this inaugural function. Let us all meet in the upcoming sessions of this program. We will take 5 minutes break, then we will go for our first session. Thank you, sir. Thank you.
Okay. Thank you. Thank you.
Thank you.
Thank you, Dr. Jivan.
Thank you.
Thank you.
Welcome. Sir.
Thank you.
Welcome.
Thank you, sir.
So, dear participants, we will start the next session by 5 minutes. Okay, the next session will be taken by Dr. Rabiul Islam from the University of Wollongong, Australia. He will be delivering a talk on multi-level inverter as a solid-state transformer for renewable power application. Stop. Stop. Rebel sir, shall we start? Rebel sir? Shall we start, sir?
Yeah, yeah,
Okay.
yeah.
Okay.
No problem. So, how to share?
Can you share the screen, sir?
So I'm looking the options. So I can't see the option.
Yeah, yeah. It is at the down.
Bottom,
It is at the bottom, sir.
there is a two option: turn on citation and present now.
Yes, yes.
So you have to click present now.
Oh, yeah, 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 yeah.
Yes, and share your entire screen.
Okay.
And sir, there is some black windows going to and share. Yes, it is coming, sir.
It is coming, sir.
So can you see my presentation
Yeah,
slide?
yes. No, yes, sir. It is fine. It is visible, sir. Okay,
Yeah.
so let me officially introduce you. Then we'll start, sir. Okay,
Yes.
so dear participants, we are going to start our very first session. So welcome you all again to our first session by Rebel Islam from University of Wollongong. Okay. So Rebel Islam received the PhD degree from University of Technology Sydney, UTS Sydney, Australia in 2014 in electrical engineering. He was appointed as a lecturer at RUT in 2005 and promoted to professor in 2017. In early 2018, he joined at the School of Electrical and Computer Telecommunication Engineering, University of Wollongong, Australia. He is a senior member of IEEE. His research interests are in the field of power electronics converter, renewable energy, power quality, electrical machine drives, smart grid. He has authored and co-authored 170 papers, including transactions journals. He has written or edited 4 technical books published by Springer. He has served as a guest editor for IEEE transactions on energy conversion, IEEE transaction on applied superconductivity, IET electrical power application. Currently, he has been serving as an editor for IEEE transaction on energy conversion and IEEE power energy later, an associate editor for IEEE Access. He has received several funding from government and industry, including Australian government ARC Discovery Project 2020 entitled Next Generation Smart State Solid-State Transformer for Power Grid Application. So may I request sir to start your talk, sir. Sir.
Thanks,
Over to you.
Dr. Amritas Kumar, for giving me the chance to present something in this short-term training program. So my title of this lecture is Multi-Level Inverter as well as Solid-State Transformer for Renewable Power Applications. So in the title, there are some keywords: multi-level, solid-state transformer, renewable energy applications. So the multi-level and solid-state transformer, these two terms or keywords actually are related to medium voltage or high voltage. Yeah. And in power transmission and distribution system, we know we used medium voltage or high voltage lines or systems where the low voltage system can be interconnected by transformer, right? Here we see this is a traditional transformer. And we know where's the application of transformer. Simply we can say an electrical device which can transfer electrical power from one circuit to another circuit without changing the supply frequency. So if we consider a very basic principle of transformer, that means it has 2 windings primary coils, secondary coils, right? And electrical energy or power transfer from primary side to secondary side without electrical connections, right? That means it has galvanic isolation. So mainly we used transformer for either voltage step up or step down. And another application is isolation. So then if we look at the issues related to the transformer, what are the problems with the traditional transformer? Is there any problem? Because this device is already well established with high efficient, high performance, right? But due to the revolution or due to the ongoing changes in our power system, some issues becoming serious. If we talk about the environmental issues, transformer requires transformer oil, which is environmental concern. And many applications, these traditional transformers are heavy and bulky. So therefore, this is the time to think about the alternative technologies. So here we see the traditional transmission and distribution network. And we can easily realize that the structure of the overall scenarios. That means here power generation, and this side, you see, most of the loads here, and this transformer just stepping off the voltage, and then transmission line, and here we see distribution line, and in between the transmission and distribution line, there is a step down transformer, right? So keep in mind, this is a very common structure of existing power transmission and distribution network. But in the future, what we will see? Okay, I'll talk on that within the next couple of minutes. So then consider the power quality problems. For example, voltage unbalance, voltage sag, voltage swell, harmonics issues. Those power quality problems, do you think can be handled by the traditional transformer? So the traditional transformer cannot handle those power quality problems. Even the transformer can be affected, the performance of the transformer can be affected by those power quality problems as well. So as the transformer cannot handle those power quality problems, therefore, in the power transmission and distribution network.
Sorry to interrupt you, sir. Sir, can you make the screen in full mode or read mode? The PDF to be in read mode. The screen is not visible completely. Like full screen, if you can make it.
Okay, so it is a PDF file. It is not PPT.
Okay, sir. You can go to View tab. I can see the View tab, sir. View tab. At the top, sir. Yes.
Okay,
yes. Yes. So there's a read mode there, sir. Read mode. Just at the top, you can search. So read mode. No, sir. Down. Yes, read mode. No. Up.
Okay.
Yes. Yeah. Now fine, sir.
Better?
Yes, it's better.
Okay, thank you.
Okay,
So,
continue, sir.
Yeah. So we need other devices or components, for example, StatCom, DVR, PQRC, and UPQC. Those sort of extra devices we need to overcome those challenges or those power quality problems. And also, this traditional transformer cannot handle power, don't have power flow control capability. And also, it can't work with the DC power. But what we are expecting in the future, in our future power transmission and distribution network, so these additional components, these additional devices, making our network bulky, making our system complex to handle. So here, I want to introduce another challenge that our transformer may or maybe will suffer by this problem. For example, especially if we talk about the large penetration of solar power, then what will happen? Solar power feeding to the grid through power electronics converter or inverter, right? So if you analyze the output power of the solar PV inverter, then you can easily realize that that inverter not only injecting AC power, it is also injecting some DC components or power. So if it is just feeding by only one inverter or only 2% of total power, then it's not a matter. But if thousands or 10,000s or more inverter feeding power to the grid, then what will happen? If we consider the large penetration, then what will happen? Then that DC power may create some problem. And even there is a possibility to reverse power flow through the transformer. If there is a large generation by solar photovoltaic power plants or solar rooftop solars, and during the daytime, if there is no sufficient or enough local loads, so then there is a possibility to flow power in reverse through the transformer. That time, these DC components may affect the performance of the transformer. That means transformer core saturations, heating effect, and then possibility to damage the transformer. So that means these sort of things we have to consider if we talk about large penetration of renewables, large penetration of solar PV, then we have to think about it. Whether our existing structure, existing devices can handle those situations or not. So that means we need to take preparation. Okay, so based on the ongoing changes in our distribution sector, people are expecting this type of transmission and distribution network in the future, right? So what we can see in this transmission and distribution network, large penetration of renewables, large penetration of electric vehicles, and battery storage, and also not only the AC network in the system, the DC networks also in our transmission and distribution network. That means somewhere DC microgrid or DC grid, somewhere AC grid. And the DC is not only low voltage in the range. People are expecting medium voltage DC as well. So based on these scenarios, what we can realize, if we want to implement this type of network using the existing technology, for example, with the traditional transformer, then can we imagine what would be the problem and how complex the whole network? Because here you see this electric vehicle just connected to the grid in between, nothing here, but originally should be there is one or two components or devices, heavy and bulky components in between. We can't connect directly this vehicle to this. We need transformer, we need power electronics, same as others. For example, solar, wind farm. So in order to connect those sources or loads to grid, we need power electronics, converter, inverter, as well as transformers. And also, in order to avoid the power quality problems, we need some other devices. That's why I already mentioned, if we go with the traditional devices, then our overall system will be more and more complex. Even it will make the system in something like really very difficult to handle or difficult to manage. Here we see some possible scenarios. That means if we want to connect solar or wind farm to the grid, what do we need? We need power electronics, converter, inverter, and also transformer. If we want to connect storage with the grid, then we need power electronics, then transformer. If we want to connect electric vehicle or electric transportation, then same thing. And we use the other power quality improvement related devices to interconnect in our substations, right? So therefore, this is the time to think about how we can make our system simpler. So then the question is, can we develop a system that means a unique device which can replace all the components here? You see, the one component to replace all the components here, including all power electronics, all transformer, and the power quality, related devices. So is it possible to replace all of these components by using a single device? Then the answer is yes. Simply if we consider the mobile phone, historical development of mobile phone, cellular mobile phone. So think about the mobile phone that we used around 10 or 20 years ago, and compare that one with whatever we can see at the moment. Now our mobile phone can handle everything. For example, many participants are using their mobile phones to listen this lecture. But you see, previously people actually used either laptops or desktops to do this job. And our current mobile phones can handle, it can be used as a camera, it can be used as a television, as a laptop, as a, yeah, it is playing many roles. So that's why we can say, yes, we can do that. So then, you see, what's the advantages if we can develop a system, something like that? That means, you see, in this system, this single device can interface multiple renewable sources, storage, and can be connected to the loads. And it has the ability to handle the power quality problems. It has the ability to control the flow of power. That means in which direction you want to flow how much power, right? And you see, it is a very just only a single unit replacing multiple units. So that's why we can make our system very rigid, very simple, which of course may help to improve the performance as well. Performance including the efficiency, because it is replacing the existing lossy and heavy and bulky components from the system. Okay, have a look the offshore wind farm. So offshore wind farm usually is installed 10 to 30 kilometers far from sea beaches, and the neckly, that means wind turbine neckly, usually installed 80 meters above the water level. So then what's the problem with this? So that means the weight and volume of this neckly actually increase the installation cost and the other factors as well. So first, have a look what sort of electrical components inside this neckly. So here we see this is a traditional system. That means we can see generator, converter, and step-up transformer. So this step-up transformer for just stepping up the voltage, this low voltage level to grid voltage level. Usually we use medium voltage to transfer this power to the main grid. So as you see here, this transformer is really very heavy and bulky. If we consider 10 megawatt wind turbine, for example, Sea Titan, it is 10 megawatt in size. So do you know how big a 10 megawatt transformer? So in order to install these components in this neckly, can you imagine how strong this tower should be, right? So therefore, those heavy and bulky components in the wind power generation system basically increase the installation cost, and also the traditional transformer uses transformer oil, which require regular monitoring. And in offshore areas, of course, we need helicopter to monitor those things. So therefore, it will increase not only the installation cost, but also maintenance cost as well. So therefore, why not to find alternative option? As I mentioned, that transformer, that means traditional transformer, basically for to step up the voltage and provide isolation between grid and the wind turbine. So if we can achieve these two things by some other devices or components, then we can eliminate that transformer from the wind turbine neckly. So then how to do that? Yeah, here you see we can consider medium voltage converter or high voltage converter instead of low voltage converter. In the traditional system, sorry, here in the traditional system we used low voltage converter. But if we can introduce a medium voltage converter, that means that converter has the ability to step up the voltage from low voltage to medium voltage level, and if it can handle the isolation issue as well, then we can connect wind turbine to medium voltage grid without a step up transformer. So then what's the technology? What sort of inverter or converter we can use to do this job? Well, you see, traditionally, people use two-level inverter. Basic concept is here. So it's, you see, basically two switching points. So therefore, we can say the output voltage represented by the blue lines or blue colors. We used a PWM pulse width modulated modulation technique here. That's why you see the output voltage from this type of inverter looks like this. So what we can see, either 200 volts positive or 200 volts negative. Only two levels, either positive 200 or negative 200. That's why it is called two-level inverter. So if we compare the output voltage with a reference signal, yeah, then you can easily realize that the difference, our target to produce this type of sinusoidal waveform, but in the reality, it is not. In this case, if we go with the multi-level topology, where you see multiple levels, the voltage levels, you see 0 to 100, then 100 to 200, several levels here. How many levels here? 1, 2, 3, 4, 5. That means 5 levels here. So in this case, you see the output voltage waveform is much closer to the reference signals. What does it mean? It means these systems not only giving the ability to design high voltage or medium voltage inverters, but also giving the chance to reduce the size of the line filters as well. Okay, I will give you more information within the next couple of minutes. So here, the multi-level output, output of the multi-level inverter is represented by blue line waveforms, and each level, it is actually composed by a number of PWM pulses, which also helps to increase the power quality, decrease the harmonics. And by increasing the number of levels, we can decrease the harmonic components. So, for example, for 11 kilovolt converter, if we used around 17 level converter or inverter, then you see the output voltage was harmonic content less than 5%, which inherently satisfy the IEEE standard. That means we can feed that power to the grid directly without using any line filter. So maybe the question you may have, like, it requires more switches or more switching components, which may increase the cost. Originally, it is not true, because multi-level converter giving you the chance to, or enabling the use to low rated devices rather than using high voltage rated devices. If you search the website or somewhere, then you can easily find that the lower rated devices are much more mature and cheaper than the high voltage rated devices. So therefore, although the number of components are increased, but the total cost is still comparable with the existing technology. So then question is, what are the inverter topologies available in this area? Well, neutral point clamp, that is the one of the multi-level converter topology. Here we see it has a numbers of auxiliary diodes. On the other hand, we can use flying capacitor-based multi-level converter topology, and which is basically composed by a numbers of auxiliary capacitors. On the other hand, the modular multi-level cascaded, this type, that just cascading of haze bridges, there is another type of multi-level topology, and here there's no auxiliary diodes or capacitors. So this one is better in terms of auxiliary devices, because the diode, it has a reverse recovery limitation, and capacitor, it is bulky, and also lifetime of capacitor is much lower. So therefore, people wants to eliminate, or people wants to avoid capacitors from the system. So in terms of those two factors, we can go with modular multi-level cascaded topology, but it requires isolated multiple DC sources. Here you see each haze bridge requires isolated DC sources. So that's the problem. Okay, so I will talk on that topic within the next couple of minutes. So here you see the output voltage waveform from multi-level converter, and this output voltage waveform for neutral point clamp, flying capacitor, and modular multi-level cascaded one. And these are from 5-level inverters, and these output voltage waveforms from 11-level converters or inverters. So here you see the output voltage waveform, I mean blue one, it is highly comparable with the reference one. That means almost, yeah, the same. And this voltage waveform, without using any line filter, the inverter or converter inherently can generate this. And here we see the output voltage waveform for different multi-level converter or inverters. This one with the 9-level, then this one with the 21-level multi-level converter. So if we use 21 levels, then you see the output voltage waveform, it is almost sinusoidal. Yeah, and its harmonic content already less than 5%, right? So if the harmonic content less than 5%, that means without using line filter, we can feed this power to grid. Okay, so then for wind power generation system, we can propose this type of topology. For example, this is, you see, the modular cascaded multi-level topology here. And as we need multiple isolated DC sources, so therefore I used here a magnetic link which can generate multiple isolated DC sources from a single source. Does it make sense? That is, you see, with this topology, we can feed this wind power to the medium voltage grid without using any step-up transformer or line filter. In this case, you see, we can eliminate the step-up transformer line filter. That means this inverter or converter can generate medium voltage output with the quality. Okay, so maybe this single magnetic link cannot handle 10 megawatt of power, right? And just for your information, this is just a magnetic link. It is not stepping up. That means turn ratio 1:1, and this one just producing multiple isolated sources from a single source, and also providing galvanic isolation. So that's why you see, as I mentioned before, if we can find a technology which can provide galvanic isolation as well as to step up the voltage from low voltage to high voltage, then we can replace the existing transformer. Yeah, here we see the multiple magnetic link based system. So in this case, you see there is no limitation of our handling capacity. All are modular in nature. So by adding more and more modules, we can increase the power handling capacity. And you see here, this wind power feeding to the medium voltage grid without any step-up transformer or line filter. So this technology already tested in the laboratory. And here you can see the experimental output voltage waveform. This is the phase voltage and the phase current. And here we see line-to-line voltages. So we implemented 1.2 kilovolt system in the laboratory. Yeah. And this output voltage waveform without any filter, no filter in the circuit. On the other hand, if we talk about the solar power generation system, so what's the traditional technique, traditional technology? So here we see the traditional system, PV inverter or PV array, then traditional two-level inverter here. And we need this type of transformer to interconnect, integrate the power and to step off the voltage to feed those power to grid. And also, as this inverter drive, the switching speed of this transformer is around 20 kilohertz. That's why we need EMC filter in both sides, yeah, input and output sides. And also, this inverter generates a huge harmonics. That's why we need line filters as well. So those filters and also these transformers, those actually makes the system complex, bulky, and less efficient. So therefore, we can think about how we can simplify the network. So maybe this is the technology that we can go with. So here you see the similar technique what we used for wind power generation system that can be used to interconnect solar PV farm to the medium voltage grid or network without using those heavy and bulky step-up transformers and also the line filters. And you see here we used magnetic link. These are high frequency magnetic link. High frequency magnetic link, those are very, very smaller in size, right? And it is just for isolation and to produce single source to multiple sources. No step up here. And this technique also implemented or tested in the laboratory, and we got very satisfactory results. And here you see the phase voltage and phase currents, and here you see the line-to-line voltages, and then corresponding. And this one, you see the TSD is not really less than 5%. That's why we need small size filters. But we actually implemented 5-level topology. Yeah, that's why we got a 15.8% TSD. But if we can implement with the 15-level multi-level topology, then the total TSD, total harmonic distortion, can be reduced to less than 5% inherently. Okay, so then how this technology can be implemented for solid-state transformer applications, or how we can use those technologies to replace the traditional transformer, right? So what's the function of transformer? Transformer, just as I mentioned, just step up the voltage or step down the voltage and isolation. And especially if we talk about the future grid or microgrid, then we can include the other advantages, other factors as well. For example, multiple distributed generations and other energy storage, and also maybe DC grid there. So whether can we interconnect or consider everything within a pack, within a single unit? Here you see, this is a high voltage side, you see, high voltage side, and this side is low voltage side. low voltage AC bus is here, and low voltage DC bus is here, and energy storage, and everything, you see, it is interconnected with this common device. This is a single device here. This part, this is a single unit, but it is interconnecting different type of sources, loads, and also grids, AC grid, DC grids, low voltage grid, high voltage grid, or medium voltage grid. Does it make sense? That means single unit which can interconnect with a number of sources, a number of loads, either DC grids or AC grids. So can be interconnected with this common device or common unit or element. So that is called solid state transformer. And we called a smart solid state transformer. If we can implement some advanced control technique, then of course we can define a smart solid state transformer. So in the beginning of this lecture, I mentioned where's the technology to replace all the components from the system, or to find a common device to replace those a number of components. So this is the technology. This is just for example. In this way, we can replace a number of components. And also, maybe you may ask how this system can handle the power quality problems. So here you see, we used to just power electronic circuit. Yeah, and here, this AC power converting to DC, then again reproducing AC here. So therefore, everything can be, totally minimized through this process. That means we just convert AC to DC, then it is pure DC. Then it cannot affected by the previous frequency. That means previous frequency or harmonics or voltage sag or swirl, everything can be minimized. Okay, so you already realized that the magnetic link is the main components in this medium voltage converter or multi-level converter or solid state transformer. So therefore, it is a big challenge to design an optimal high frequency magnetic link. And also it is a challenge to find and the good magnetic materials which has high flux density and low core losses. So in terms of flux density, the amorphous and nanocrystalline, those two materials are really superior than others. For example, amorphous, its maximum flux density, it is around or more than 1.4. Whereas if we compare with the ferrite, it is about 0.4, 0.5, or something like that. So therefore, we found amorphous and nanocrystallines are the ideal materials for these applications. We already developed many codes and tested in the laboratories. And also, in order to design the solid state transformer and the medium voltage converter, the design parameters of the magnetic links are very important. Based on that, we have to have select the control parameters. So here we just developed a system to interconnect a wind turbine to the medium voltage grid. And here you see the wind turbine, then this magnetic link, then our converter or inverter here, and it is fitting to this medium voltage grid. And we simulated this technique, and also we implemented in our laboratory environment. And we also consider different real scenarios. For example, voltage high, and as well as voltage swell, voltage sag, and other unwanted situations, for example, harmonics and those sort of things. And we found those challenges, those actually problems can be handled, can be minimized by these solid-state transformers. But it requires sophisticated control algorithm or technique. And also, as you know, this multi-level converter or this medium voltage converter or this solid-state transformer basically consist of a number of Haze bridge modules, or you can say multiple Haze bridges. So in order to control the flow of power, definitely we need some coordinated control technique or algorithms. So we developed some control algorithm or techniques to overcome those real problems or existing problems in the power grids. So, and also investigated how many bridges, that means how many Haze bridges can be connected, or how many sources, how many loads can be connected in a magnetic link, and how to control the power flow, and what's the factor that actually affect to control the power flow. And here we see we actually investigated with the DAP, dual active bridge. That means only 2 bridges there. And also we consider 3 bridges, and also 4 bridges, and also 5 bridges. Then we also compare the power handling capability. That means the optimal design. In order to find an optimal design, we have to find the right number of bridges on the magnetic link. And based on that, we have to select the control parameters from the magnetic links. Yeah, we already implemented those sort of control techniques, and also those sort of ideas to improve the performance of the solid-state transformers. And another important thing is the thermal issue, which is really very important for power electronic circuit, especially for this type of converter or inverters, where hundreds or thousands number of power electronic switches are used. So therefore, the proper thermal modeling is important. So we already actually introduced some techniques to model the thermal behavior based on the switching algorithm. And from those models, we can then design the heatsink or other productive circuits or components for the system. Another thing is the power handling, the power loss equalization among the switches. That means we have to make sure whether all switches are handling equal amount of power and the losses or the thermal or temperature generating or generated by the components or switches are equal. If there is an inequality between the temperature generation by the devices, then the lifetime or lifespan of the whole system will be different. So in this case, in order to confirm this, we need some techniques to confirm all devices in the system are distributing the same amount of power. So this is my presentation. Thanks for your.
Thank you, Rebel. Okay, so I am presenting some of the questions that participants have asked.
Okay, yeah.
Yeah, you can stop presentation, then I can share you the screen. Or I will do one thing. Can I post the question in the chat box? Then you can answer.
Yeah, sure.
Okay. So I'm posting some questions. So I'm just posting it. You can look at the chat box. Like.
Okay, yeah. So I can see it now. We use SSD application for electric vehicle circuit design. If yes, what are the key points to be considered, as it is DC to DC type boost from okay. Yeah. So someone just asking about the use of solid state transformer for electric vehicle application. Right?
क्या? हाँ मैं मीट में डाल रहा हूँ, ठीक है?
Okay, so for electric vehicle, you say its power rating may be around 30 kilowatt, and in this case, yeah, that is one time. As I mentioned, solid state transformer, it's not a unique structure. It can be any structure, and it can be used for any applications. So therefore, why not? We can also use this one for electric vehicle applications. And how to design harmonic compensated multi-level inverter for renewable energy applications. Harmonic. Yeah, so now you see for multi-level inverters, although it can inherently provide quality power, I mean, in terms of harmonics, but still many people are offering or introducing different type of modulation technique or algorithms to improve its performance further. So, for example, bus clamping or third harmonic bus clamping, 60-degree bus clamping, those sort of things. And also third harmonic injected, those things are very popular. So, yeah, we can do that. And I'm reading the another questions here. What are the losses are in solid state transformer as compared to normal step down? Okay, so as I mentioned, solid state transformer actually going to replace a numbers of devices from the system. Not only we can't compare this one with the traditional transformer. So we have to consider the whole situations. I mean, total system. For example, solid state transformer can replace existing transformer, line filter, inverter, and many more. That means we should consider 4-5 other components if we want to compare that losses. So that means we have to consider the losses of the line filter, losses of the inverter. I mean, existing system use 2-level inverter, then line filter, then transformer. So we are replacing 2-level inverter, line filter, as well as transformer. Does it make sense? That's why you see still the efficiency, it is comparable with the traditional system or even better. So, okay. So electromagnetic interference issues, someone asking about, actually mentioned about the interference issues. So interference, you see, multi-level is the topology with enabling to use load switching speed. The interference issues, you see, in the existing system, we are still using 20 kilohertz inverter, right? So same problem already there. So therefore, people are using electromagnetic interference filter there. In this case, our inverter may use lower switching frequency. That means we can go with 5 kilohertz or even 1 kilohertz. So compared with the existing 2-level system, this inverter uses lower switching frequency. But for the high frequency magnetic link section, at the moment we are using 5 kilohertz to 10 kilohertz. So still it is within the normal range. Normal range means whatever people are using in the existing inverters. So then so can multi-level inverters be used for residential level power inverters for PV grid connected systems? So residential, you see now we used low voltage system, right? So multi-level basically for medium voltage or high voltage applications. So therefore, it is not really suitable for low voltage, I mean 230 or 400 volts applications. But why not? We can use it. But it is really suitable for medium or high voltage applications. So test of multi-level converter of 3 has pieces 18.3%. Shed some light of filter components obtain better response. So as I mentioned, multi-level converter its switching frequency can be reduced because it has two, options to improve the performance. For example, if you look at the output voltage waveform, so then how we can reduce the harmonics in the traditional inverter, just we have one options to reduce the harmonics. That is, by increasing the switching frequency, we can reduce the harmonics. But for multi-level, we have another options. That is, without increasing the switching frequency, if we increase the number of levels, then harmonics will be decreased. So that means without increasing switching frequency, still we have the chance to, or still we can reduce the harmonics by increasing the number of levels, output voltage levels of the converter. What is the percentage reduction in size and weight of receiving using SST compared to the traditional system? Okay, yeah. So as I mentioned, the solid state transformer is still, it is an ongoing project, and many people in the world from the different countries actually trying to improve the performance of this technology. So, and also it has no unique limit, structure. So it can be any form, any structure. It depends on the applications. If we consider it is for wind farm, then it's different. It's for solar, then it's different. If we talk microgrid, then it's totally different. And also for the distribution grid, for example, just for step up or step down, no other renewable sources there, just only, then that's the different. So therefore, it depends on why we are going to use this solid state transformer, right? And what sort of functions we are considering here. As I mentioned in the beginning of this lecture, so this, although it's named with a transformer, but it is not actually replacing only transformer. It is going to replace a numbers of components from the systems. So therefore, definitely, it is much more compact, smaller in size, lightweight, efficient, and definitely this device can make our system or grid smarter.
Okay, so I think this is all about the questions from participant. Rebel sir, I am having one question from my side.
Yeah.
That is basically we are using solid state transformer. So basically at the interface we are having this like DC to AC inverter, so many connected. So for transferring power from one converter to other, which control, like it's control based on phase shifting or any other control mechanism you are using?
Yes, actually, no, phase shifting is a very popular technique. Yeah. So, and also definitely we can use the other control technique as well. But phase shifting is a very common one. So, but phase shifting, you see, just if we use just only phase shifting, then if it is a depth converter, then only phase shifting is enough. But if we have multiple, sources there, so definitely we need some sort of other mechanisms. Especially the control that is called coordinated control. We already mentioned there, and we already published some papers on that. That means how to control, coordination which section of the circuit actually handles what percentage of the power. So in this case, you see, for example, 4-quadrant operation or 2-quadrant operation of the converter. So therefore, it actually depends on the control signals or switching signals.
Okay, sir. Okay, sir. Thank you, sir. Thank you once again, Dr. Rebul Islam, for such an informative lecture addressing different aspects of starting with the normal transformer, its shortcomings, the leg size, weight, how we can minimize the size and weight using solid-state transformer. Thereafter, some experimental setups that you shown. It is really inspiration for all of us to do something on the hardware with its control. That is the very important part that Gorilla sir has discussed in the in the inaugural session, that we should have the modeling, that is simulation, and the control, that too on an embedded system. So you had a combination of all. So it's great, sir. Thank you for such an informative session. Thank you once again for accepting our invitation, for being a part of this as an expert in this STTP. Sir. Thank you once again, sir. Thank you.
Thanks.
So,
it
thank
is my
you.
pleasure. Thanks.
Thank you, sir. So, dear participants, we'll again meet at 2 o'clock for a next session by Dr. Gurunath Gorela from IIC Bangalore. So, he's going to deliver expert talk on realistic experimental testbed for microgrid and smart energy system. So, please attend the session at 2 o'clock. We'll meet again at 2 o'clock. So, now all participants are requested to fill the feedback link, like already been like shown in the YouTube link. So you please fill the feedback. It's going to be over by 10 minutes now. Okay, so do fill the feedback. Thank you, sir. Thank you for joining. Thank you.
Thank you. Bye, everyone.
Bye bye. Namaste, sir. नहीं पहले वो पहले रेस्पॉन्स का खत्म हो जाएगा तब